To understand loops, to reason about loops, we need to understand the fundamental notion of loop invariant. Every loop, and I repeat, every single loop has an associated loop invariant, and to convince ourselves that the loop is correct, that is to say, that it fulfills its goal, we need to find what the invariant is and to check that it is indeed an invariant. Syntactically, the invariant appears here. We've seen the basic form of the loop, but if we want to have the full form, it includes an invariant and a variant. The variant will be seen in the next lecture. It allows us to check that the loop terminates, and the invariant appears just after the from clause, and it enables to check that if the loop terminates, then it fulfills its intended goal. The invariant clause, as well as the variant clause, is optional, but it's strongly recommended that you include it whenever possible. It introduces an expression, and that expression is a Boolean expression. This is, as in the case of class invariants that we have seen for classes, but it's a different kind of invariant. Here's an example. We have a loop whose purpose is to find out what is the name of the station on line 8 of the metro that has the highest name, highest in the sense of alphabetical order. So ABC is less than BCD, which is less than XYZ, and of these three, XYZ is the greatest in alphabetical order. We're assuming a function greater, which given two strings tells us whether the first one is greater in the sense of alphabetical order than the second one. So greater returns true if and only if, in this case, result is greater alphabetically than the second expression, line 8.item.name. So you see the loop. It starts at the beginning of the line. It moves the cursor to the beginning. Then it initializes the result to an empty string, and for an empty line we will accept that the result highest name is just the empty string. It loops until we are at the end of the line, and each step through the loop, before of course doing the force, it updates result by the greater of the previously computed result and the name of the current station. The current station is line 8.item, and the name of that station is line 8.item.name. So this loop is quite clear. I'll give you a minute to look at it more carefully, but it should really be self-evident, and it gives us the greatest of the names of all the stations in the line. Or does it? How do we know that it really works? Well, in order to know that it really works, we are going to have to exhibit an invariant which enables us to have a logical argument, not just a kind of informal argument, as I just gave, that the loop does what it's supposed to do. So here is the invariant. The rest of the text is the same as before, the from, the until, the loop. What's new is the loop, the invariant part, and it tells us that each time through the loop, that's basically what invariant means, each time through the loop, it is true at the beginning and at the end of the iteration that the index is at least equal to 1, that the index is also less than or equal to line 8.count, which, as you will remember, is the number of stations in the line 8.count, and also an informal part of the invariant, which in fact is quite important to determining the result, namely that result is the alphabetically greatest of the names of all previous stations. Now, before we go a bit further in this, there's actually a trick here, and in the sense that this invariant is wrong as I've written it, and I'll give you a hint. It's wrong in one of the first two lines, so I'll give you a second to find out what indeed is wrong. Well, if you followed carefully, you will have noted that I said that the invariant has to be true before and after each iteration of the loop. And if you think of the last iteration of the loop, then of course it is no longer true at the very end that c.index, the position of the cursor, is before the last element of the loop. In fact, it will be one position after. If we have the list here, the last time through the loop, before we can find at c.after holes, we are going to move the cursor one position, and so c.index will be line a.count plus 1. So you see how careful we have to be. Of course, this is only in the invariant here. It doesn't affect the execution of the program, but it's typical of the kind of by one, as it's called, mistake in reasoning that can affect programs as well as assertions about programs. So we really have to be careful. Okay, so sorry for playing this little trick on you. Let's get, now the invariant as it is written is indeed correct, and more precisely it is what enables us to find out that the loop is correct, that it computes what it's supposed to compute, that is to say the alphabetically greatest of station names. You see, by the way, that the invariant is expressed in a kind of mix of formal properties and informal ones, the second one being a comment. Well, this is often how we have to express invariants unless we go towards full formal reasoning about programs, which we're not prepared to do yet. But still, it's quite clear what is being expressed here. The index will always be at least equal to 1, at most equal to count plus 1 of line 8, and the result will at each step be the alphabetically greatest of the names of all stations considered so far. So this is what the invariant is. It tells us what is true during the loop. More precisely, as I mentioned already, before each iteration and after each iteration of the loop. And then at the end, once we have explored all stations, well, it gives us the final result, which is that that result is the alphabetically greatest of all station names, since we have seen all stations. So this is how we reason about the loop. We exhibit an invariant which is a kind of weakened or partial version of the property that we're trying to achieve, weakened in the sense that it only applies to a subset of the problem. In this case, a subset of the data structure that we are traversing, but we keep it step by step, and then at the end, having increased its scope little by little, it will give us the whole answer that we want. So we can illustrate this idea graphically. Let's consider the list of stations, but actually, since we're interested in the station names, I've only here represented the names of the station, name 1, name 2, and so on. So what do we do with the loop? Okay, remember the loop. At each step, we compute the greater of the current result and the current name, which we haven't seen yet, and we advance by one position, c.force. Well, so let's see this graphically. Here I have pictured the list of stations, but more precisely, since we're interested in the names of the stations, I've pictured the list of names of stations, name 1, name 2, and so on. So what does the loop do? Well, at each step it's going to include one more element of this list. So the first time around, after the result having been initialized to empty, if the list is not empty, we assign to result name 1, since it's going to be the greater alphabetically of name 1 and empty string. Another way of expressing this is to say that result, as it is the maximum of the slice of the sequence of names, name I, the slice from 1 to 1. So you understand this notation. I'm going to have to express names I ... j to mean the slice, the subset of the sequence or the subsequence from I to j. This is going to be represented as names of I ... j. So what we have here initially is a trivial slice, the slice from 1 to 1. So we can express the result after the first iteration in this way. Now we encompass one more element in the second iteration of the loop. And so as a result, since we take the maximum of the result computed so far and name 2, the greater of the two, we are going to get max of names of the slice 1 to 2. And so that's the property that we're maintaining at each step, the fact that result is the max of the slice seen so far, 1 ... I, where I is the last station that we've seen. So we go to name I, someplace in the middle of the list, and the property that we have at this point is that result is the max of names the slice from 1 ... I, and that is the invariant. And the purpose of the loop body is to maintain that invariant. That is to say, if we execute that loop body which increases I by 1, well, the invariant is not going to be satisfied anymore, or is not necessarily going to be satisfied anymore, because name sub I plus 1, which is the new name sub I, the old name sub I plus 1, which is the new name sub I, might be greater than the previous result. So in order to restore the invariant, we have to update result to be the greater of the result computed so far, which is the max of the previous slice, and the name of the current station, which is line 8.item.name, and which on the figure is also name sub I. So this is how we work. We restore the invariant, and we can see that the invariant characterizes the loop. We could also look at it from a different perspective, and to say that the more fundamental property is the invariant, which is what we're trying to keep by increasing I repeatedly, and the purpose of the loop is to preserve, in this case, to restore the invariant. So we can look at it either way. Either we start with the program and use the invariant to help convince ourselves that the program is correct, or we say that actually the specification, the invariant, is more important, and the program is just there to fulfill the specification. In the end, it doesn't matter that much which viewpoint we take. What's important is that the loop and the invariant of the loop are closely related. And so what happens at the end is that since we have increased I repeatedly until I is equal to n, then since the invariant still holds, we are going to have the property that result is max of the slice going from 1 to n, and of course that slice is the entire sequence, the entire list, and this is exactly what we wanted. So that is the reason why the loop is correct. Now you might say that you'd seen this all along, but this is the formal way of convincing ourselves that the loop is correct. We understand now why the loop is correct, not just informally, but formally using logical techniques. And it is so easy with loops in particular to make small mistakes that are going to result in a wrong program, that we absolutely need these formal ways of reinforcing our confidence in the correctness of our software. Here's an illustration of what the invariant is about. It's just an illustration. It's a kind of metaphor, so you may or may not find it useful. I find it useful to understand what the loop is about. It provides a good illustration of how a loop process proceeds. So we're looking for a solution. Now, in general, a problem may have more than one solution. So that's why I'm picturing the solution here, not just as one point, but as a little interval which contains all the solutions that would work for us. Of course, it might be just one point. Now, we don't have the solution right away. Otherwise, there would not be any need for a loop. But what we do have is a much broader region of states for a possible program that we know encompasses the solution. And that region is the place where we are going to play, so to speak, and it's the invariant. So we're going to stay in the invariant and try to get closer and closer and closer to the solution. And the way it works is that we define the solution as the intersection, so to speak, again in that metaphor, between the invariant, the yellow part, and the exit, and some condition, some other region which corresponds to the exit condition, the green part here. So the general scheme for a loop is to try to land somewhere in that region and then reach the nirvana of the desired solution. So let's see this process at work. Before the loop computation, the state of the computation was somewhere, represented here at the bottom left, and then we try to land somewhere in the invariant. That's the initialization. How is it called in Eiffel? What is the corresponding syntactical clause? Yeah, you got it. It's from. That's the purpose of the from. And from a formal perspective, it's there to ensure the invariant initially. The invariant, of course, has to be satisfied initially. And then once we are in this yellow region satisfying the invariant, we never, of course, want to leave the invariant. We are going to stay in it. And we are going to try to get closer and closer to the exit condition by executing the body. And the body is there to get us closer to the desired solution. So we execute the body again, until we reach our goal. This is very similar to the kind of things that you'll have learned in mathematics for a sequence that converges. The big difference, though, is that in dealing with computers, we are producing computations that must end after a finite number of steps, maybe a very high number of steps, in the millions or tens of millions or more, but still the number of iterations must be finite. When you studied sequences in mathematics, you saw that all that really counts is that a sequence has a limit which can be reached after an infinity of iterations, although we don't necessarily call them iterations in mathematics, we call them just elements of the sequence. But with computers, of course, we cannot afford to have an infinite sequence. We have to reach the result after a finite number of steps. And this will be the purpose of the variant, which we see in the next sublecture. What really matters is that you see that for any loop, there is an associated loop invariant which characterizes the correctness of the loop. It's a similar notion to class invariant, but of course it should not be confused with it. We have seen the class invariant which characterizes the correctness properties of a class and all its features. Here we're talking just about a specific loop. What is a loop invariant? Well, we've seen it informally. It's a property that has to be satisfied after the initialization, in Eiffel the from clause, and which is such that it's preserved by every loop iteration. Preserve means that if it was satisfied before the execution of the body, if we have this loop from something until something loop something, let's call it B for body, then whenever the invariant is satisfied at position 1, the execution of the body must restore it at position 2. That's what we mean by preserve. If it was satisfied before, it will be satisfied afterwards. It might, by the way, become temporarily invalidated during the execution of B, like here. But that's okay, as long as it's satisfied again at the end of the execution of B. Now, to be more precise, and it's written on the slide, we don't need B always to preserve the invariant. We only need B to preserve the invariant if C is not satisfied. Because if C is satisfied, we don't care, since we don't execute B as part of the loop, so it doesn't really matter. We only need B to preserve the invariant if the exit condition is not satisfied. A little later, we'll learn to write this in the following way. It's very convenient. If I is the invariant, we can say that if I is satisfied and C is not satisfied, then the execution of B must result in a situation in which I is satisfied again. This is what we mean by B, the body, preserving the invariant in initial states in which C is not satisfied. At the end, of course, C might be satisfied or not. If C is not satisfied, it means we're going to have more iterations of the loop. If C is satisfied, then the loop will terminate. But what matters is that the invariant will still be satisfied. So here again is the invariant, and we can actually write it more formally if we want to, using this notation max. Of course, we would have to define the notation max formally, but that's not very difficult. So if we want to avoid having this invariant clause in the form of a comment as here, we just have to define the function max and make sure that that we express the invariant as follows, as shown here, and it's going to be the same thing for the result. We can also express the result as result equals max of names one dot count, or line dot count. It's also interesting to note that this loop is correct even if the list of stations is empty. So this is the only difference here. We have added if any, and you can check that in this case the loop is still correct, with the understanding, of course, or the convention that the maximum name of an empty list is the empty string. Now, as to the effect of the loop, it's very simple, since the loop is going to terminate when the exit condition is satisfied. But at that time, the invariant will be still satisfied because the invariant is satisfied after the initialization, and then it's preserved by every iteration of the loop, of every execution of the body. And of course, the execution of the loop consists of executing the initialization and then executing the body 0, 1 or more times. So if every one of these iterations preserves the invariant, we know that at the end, the invariant will still be satisfied. And so at the end, the invariant will hold and the exit condition will hold. So all stations will have been visited because of the exit condition, C dot after, and result is going to be the greatest of their names, which is the outcome that we want. So what we've seen is that a loop is characterized by an invariant. The invariant is key to establishing that the loop is correct. The invariant holds initially and must be preserved by every iteration, at least when the exit condition is not satisfied, so it still holds on exit. And on exit, the exit condition also holds, so the conjunction in the Boolean sense of AND, the conjunction of the invariant in the exit condition gives us the effect of the loop. Now, for the bad news, if you want to be sure of your program's correctness, you have to find the invariant. And usually it's not that hard. You've seen in this example that the invariant is a kind of weakened version of the post-condition, of the final condition of the loop. The post-condition was that result is the maximum of all stations, and the invariant, well, the invariant is just a generalization of this. It says that the result is the maximum of the names of all the stations visited so far. So it's not that difficult to go from the maximum of all the names to the maximum of all the names seen so far. And typically this is what the invariant is, but you have to reason about your loop and try to see what the invariant is in order to be able to convince yourself that it is correct. And certainly we all want our loops to be correct.